Sleep has many effects on the body. So in particular, we'll be focusing on things that happen during non-REM sleep. And so we've got a quiet level of activity. Our organ systems usually maintain quite a steady state. And then the trick is, as REM sleep comes in, we've got that irregular activation of different body systems, and we've got the fact that we've got muscle paralysis so as not to act out our dreams. Importantly, we also have non-responsiveness to feedback at a much higher level. And so by that we mean non-responsiveness to the environment at a much higher level in REM sleep than we do in non-REM sleep. Once again, that central nervous system consists of the brain and spinal cord. So here we have the brain, a ventral view of the brain. So these are the olfactory bulbs coming off along with the cranial nerves, our spinal cord, and the nerves coming off the spinal cord. So in general, what's happening in non-REM sleep is we've got lower rates for metabolic rates and activity than we see during waking. And that's really going to fuel some of our theories that non-REM sleep really is about recuperation and rest. In Chapter 5, we talked about the differences between tonic and phasic REM. We had different tonic and phasic REM on cell areas. And for tonic REM sleep, we've got some of the brain areas just simply being more active in general. And then during that phasic, we have some areas that come on and come off, especially visual areas, can be very active at times and then be very quiescent or quiet at other times. Now, our nervous system consists once again of that central nervous system, the spinal cord and brain, and then what we call the peripheral nervous system. And the peripheral nervous system consists of neurons where the cell bodies, and the cell bodies are where the genetic material, the nucleus are. Those cell bodies exist outside the brain and spinal cord. Now, typically the peripheral nervous system is going to communicate or synapse with neurons in the spinal cord and brain, but we have to bring information in from the exterior, and then we also have to relay information for how to control muscles and glands. In your peripheral nervous system, you have what we call the somatic nervous system, which is the nervous system that we're consciously or voluntarily aware of. So if I move on my bicep, I curl my arm, that is a function where I'm in control and it's voluntary. But then we have the autonomic nervous system. We typically don't think about the muscles or glands of the interior part of our body, like our digestive tract, our stomach. We don't think, I have to breathe in now, I have to breathe out. So our diaphragm, our lungs, all of that is running on automatic. And the trick becomes that that automatic system has to have two set points. What is happening under stress, the sympathetic nervous system, and the parasympathetic nervous system is what happens in the opposite end when we're relaxed, when we're resting and recuperating. So in other words, the autonomic system, for example, my stomach, if I'm running away from a tiger, doesn't matter if I happen to try to digest that donut I just ate. So what I'm going to do is I'm going to shut that digestive system off under sympathetic nervous system control. So in other words, the sympathetic nervous system is just innervating or communicating with the same glands and muscles as the parasympathetic nervous system, but it flips it to what is needed under the fight or flight situation. The parasympathetic nervous system, I do need to digest that donut. I'm not stressed. I need that energy for later. And so the parasympathetic system would essentially control the digestion and allow it to be more active when it's not in the sympathetic state. Okay, so sympathetic or somatic, the somatic nervous system, that's our voluntary control. Our autonomic sounds like automatic, and so our autonomic nervous system, intestines, glands, our spleen, our kidneys, all that stuff, autonomic nervous system. Sympathetic control when we're in the fight or flight setting, and that's going to use norepinephrine. Remember our neurotransmitter from chapter 5 that has a lot to do with vigilance, and vigilance is about being aware of your environment, and acetylcholine, which once again is an activator. It's in high levels in the waking state and controls the motor neurons that control muscles. Parasympathetic, that's going to be about rest and recuperate, maintaining and adding to our body reserves. Now, this once again is an idea of all the different things we're talking about that need to be innervated or controlled by neurons and by neuronal activity, or neurons communicating information from the brain and spinal cord. And it's things like your heart, your pancreas for insulin, your adrenal gland for cortisol, your liver. All of that has to have activity that's controlled. Either we're going to shut it down because it's not important for immediate survival under sympathetic nervous system triggers, or we're going to have to actually use those systems, turn them on for rest and recuperation under parasympathetic. Now, here's the thing to remember, and all these lines indicate neurons, by the way. The sympathetic nervous system is really fast at turning everything to the flip switch of sympathetic nervous system. It is all connected very quickly through what's called the sympathetic chain. It's not something you need to remember for this class, but that's why it's so easy to get angry or scared or upset, and you just feel your heart racing and your lungs, you're breathing fast, and your stomach may shut down, your stomach will stop. All of that happens really quickly because it's important for survival for it to be coordinated and for it to happen quickly. Calming down, on the other hand, takes time. It can be a challenge because it's not that important for survival. Yes, we need to keep calm and recuperate over time, but doing it at speed is not important. So your body doesn't have it set up to be a speedy response, and that can be why it's difficult to relax sometimes. It can be difficult to relax and fall asleep. Okay, so just as you would expect, non-REM sleep is associated with increased parasympathetic nervous system activity. So we have to have low sympathetic activity. It's very rare you fall asleep when you're running away from a tiger. And so when you're angry, when you're upset, that sympathetic nervous system, that's going to keep you awake. Now the trick becomes, during REM sleep, we're going to need to activate certain parts of that central nervous system. I think we've all had scary dreams. Well, that's going to activate some components of the sympathetic nervous system. And so under tonic REM sleep, we're still not activating the sympathetic nervous system. But during some phasic components, maybe like a bad dream or a really good dream, that sympathetic nervous system may increase our heart rate and our breathing. Now, in general, that means that parasympathetic nervous system activity under non-REM, heart rate's going to be slow, blood pressure is going to be low, and then under phasic REM, that'll become a variable. Same thing with breathing. Now, one of our challenges becomes, because muscles relax in non-REM, that means that airway pressure, your airway can start to compress because the muscles aren't toned, and that means airflow or breathing might become a problem for some individuals. Tends to be worse for men, tends to be worse for individuals who are overweight, tends to be associated with aging, just, all the things that muscle tone could influence, anything that compresses or changes your airway. And by that I mean your throat. And they just released a study actually to show that the size of your tongue is also a big deal. So as you gain weight, your tongue also gains weight, and your tongue can slide back as you sleep and block that airway. So another big problem for keeping and maintaining a normal breathing pattern. We'll talk more about that. That's a condition called sleep apnea. Some of you may be aware of it, and we'll talk more about it in later chapters. Now, you don't cough during sleep, so that's a dead giveaway if someone's faking sleep. If you do have to cough, your body will wake you up. You may not even remember awaking when in the morning, but you're going to wake enough to cough, and then you'll fall back to sleep, hopefully. Now, REM sleep can be associated with increased activity in sex organs, and sometimes, particularly in adolescence, that can occur in non-REM. And by the way, orgasm is a very weird kind of, we have to have relaxation, the parasympathetic nervous system in control during the build up to orgasm, but then at orgasm, sympathetic nervous system activity kicks in. So it's a very weird balance that has to happen there. Okay, so we're going to see body temperature be kind of maintained, though it's lower than normal. The hypothalamus is going to function as our body's thermostat. And then the trick becomes brain temperature is going to increase during REM sleep. And that's because of that high neural activity. But the trick is the temperature isn't regulated during REM sleep. We lose that ability. And that means that the room temperature actually affects the quality of REM sleep more than it affects non-REM sleep. Because in non-REM sleep, your body's doing its thing, your brain's at kind of a low level of activity, maintaining that body temperature to a certain degree, even though we do reach our lowest body temperature. But then in REM, no control over it. Isn't that amazing? Oh, and when we're warmer, body temperature increases, may actually increase the length of non-REM deep sleep. And there's some debate about why that may occur. So one of our challenges with the sinking of body temperature is that if we don't match our body temperature to our sleeping time, or more appropriately, our sleeping time to our body temperature, we may have difficulties. So for example, when we try to nap earlier in the day, when our body temperature is still warm, we may have difficulty falling asleep, except during that mid-afternoon drop in body temperature when we actually do get sleepy. And then if we try to work at night, we may find that our body temperature is dropping, so it's easier to get cold at night if we're trying to work through the night on an all-nighter. And so body temperature definitely plays a big role in the interaction. Body and brain temperature clearly are influenced by our sleep-wake cycle. What else do we have for our body? Hormones, that endocrine system. So hopefully you remember endocrine means it's the hypothalamus controlling the pituitary. The pituitary releases more control hormones that then go to various places in the body to release all the different hormones that are chemicals that are going to travel to different places in our body and do their thing. So for example, our sex hormones. Our sex hormone controls hypothalamic, the pituitary. It then releases compounds that go to the ovary in females and the testes in males and cause the release of estrogen and androgens like testosterone. The adrenal cortex is the target of pituitary hormones when you're under stress, and the adrenal cortex releases cortisol. In other words, so the pituitary releases some hormones like prolactin and growth hormone, but other structures release hormones as well. So the pancreas releases insulin, the adrenal gland once again releases cortisol, and the thyroid gland releases thyroid hormones. So it's an intricate system, but all these hormones start with one place, the hypothalamus, and we know that the hypothalamus is intricately linked to our sleep-wake cycle. The hypothalamus is going to send messages to the pituitary. The pituitary is going to trigger the release of growth hormone, and that growth hormone's going to go to muscle, bones, and fat cells and cause growth. And in fact, growth hormone stimulating cell growth that is enhanced during sleep. So sleep triggers the release of growth hormone or is associated with it. And especially that deep wave sleep increases growth hormone, especially in adolescents and young males. And then unfortunately, as we get older, we see a decline in that growth hormone levels with our sleep cycle. So it looks like growth hormone probably might be tied to sleepiness or circadian rhythm. It's definitely affected by changes in our sleep schedule. What about the sex hormones? Once again, we're going to have the hypothalamus release a compound, in this case, gonadotropin releasing hormone. You don't need to know that. To the pituitary. The pituitary is going to release LH and FSH, luteinizing hormone and follicle stimulating hormone. That's going to go to the gonads, which is the general term for sex organs. So that's going to be the ovary in women. It's going to be the testes in men. We're going to release our sex hormones. And here's the cool thing. Those sex hormones, and this is true of all our endocrine systems, they're going to feed back to the brain, and the brain's going to be like, I got enough of this, and it's going to stop the hypothalamus from continuing release, because we basically, endocrine hormones or hormone cycles are cycles, and so we ramp up and then we shut down. So we see that sex hormone release is increased during sleep, inhibited by wakefulness, and in fact progesterone, which is a sex hormone, actually promotes sleepiness and sleep, as does estrogen. And that may be why some women in menopause, when we see estrogen and progesterone levels dropping, have difficulty falling asleep. What about cortisol? Once again, it's a hormone. So we're going to start with the hypothalamus. We're going to head to the pituitary. The pituitary is going to release something, in this case, ACTH. So all of these things are actually compounds. Corticotropin, releasing factor. ACTH is adrenocorticotropin hormone. But I don't want to test you on that. And I'm not going to. I just want you to understand that it's a sequence of chemical signals. And then it's going to reach the adrenal gland, and cortisol is going to be released. Cortisol is the stress hormone, essentially. So when we have a fight or flight response, that is the sympathetic nervous system turning on, that's immediately due to norepinephrine and epinephrine. Compounds that are neurotransmitters, but also hormones that exist in your body. Now, if you need a more sustained response, so you're running from that tiger for more than 5 minutes, then your body needs to do more. And cortisol is that hormone. So cortisol is going to go to many different places in your body and try to release stored glucose. And it's also an anti-inflammatory, so it's going to stop inflammation or your immune system. It's going to start to redirect some energy that needs to go into a stress response. And it's also why, unfortunately, we see in highly stressed, chronically stressed individuals where they're not physically working through that stress, that we see some long-term decrements. We see increased heart disease. We see problems with the immune system. And so cortisol is designed to help for 10, 20, 30 minutes, and then it's going to go up and shut the system down. And that's what you need, a nice responsive response to stress that stops eventually. Well, if you're stressed, remember this is a system that is triggered essentially at the same time that the sympathetic nervous system is triggered. Well, we're not going to sleep very well. And so elevated cortisol is associated with wakefulness. And in fact, your cortisol levels are highest in the morning, and that may be in an attempt to help your body prepare to essentially rise from a prone position, stand up, and have blood circulating and normal blood pressure levels. We also have hormones like prolactin. You may be familiar with prolactin because it helps with milk letdown in women when they're lactating, when they have a baby. And it's also sometimes associated with orgasm. But prolactin is strongly influenced by sleep, and so slow wave sleep, our non-REM sleep, really increases prolactin in everyone. REM decreases it. We've already talked about melatonin acting as a body-wide Zeitgeber to a certain degree, and it too varies across the day because across your cycle, across the daily cycle, because of course that's what a circadian rhythm is. So your melatonin levels have to shift over a cycle in order for your body to understand the circadian rhythm. And there's mild suggestions that exogenous or externally administered, so taking a pill of melatonin, might have some effects for sleep onset and sleep maintenance. And so the thing to remember is that the sleep period is about coordinating all these different hormones. That hypothalamus does a lot of work. And so we've got melatonin increasing in the evening, helping communicate that it's time for sleep. Growth hormone being secreted in the early phases of deep sleep and non-REM. In REM sleep, we've got our dreams, and then cortisol is going to rise in the morning as it tries to help us get awake, essentially. And that's not it for hormones. You would think, perhaps it would be, but there are more. We've got the thyroid hormone system. So thyroid hormones are associated with metabolism, and we've got them reaching a peak in the evening prior to typical sleep. Insulin's also a hormone. Insulin levels are elevated during sleep. Insulin's your energy, basically energy storage. So as you are sleeping, your body is trying to store energy. And it's also decreasing your appetite, and it's slowing down digestive processes. So this is a graph, not from your book, from a different one, that shows essentially we've got our body temperature changes cycling through a typical daily cycle. Our growth hormone elevating very highly in non-REM sleep at the beginning and then coming down at low levels of activity. And our cortisol needing to be very low so we could fall asleep. And notice we have fluctuations through the day, but needing to be low and then rising before morning as we're waking up and trying to elevate ourselves out of bed.